Hiya ladies and gents, let's give you some test feedback. Sorry we didn't get time to do this in school for you. So first question, looking at this little bit of information here should take you on to why we keep them in oil. So that's anything along the lines of to protect them, stop them reacting with oxygen, stop them reacting with water, stop them reacting with the air even from the external area. In terms of balancing the equation, it's the same for all the group 1 metals. It's always going to be 2 of the metal, 2 of the water, 2 of the sodium hydroxide, which means there is 1 of the hydrogens, so it's a 2-2-2-1 ratio. If you want some help balancing equations, come along and see me at some point and we can help you out a little bit with that. Part C, not usually well answered. Explain why they're all called alkali metals. It's not because the metals themselves are alkalis, it's because they react to form an alkaline solution of, for example, sodium hydroxide or lithium hydroxide. For D, in terms of electrons, it's down to the size of the shells. So when we're looking at sodium and potassium as examples here, potassium is further down the group, so you get your first mark by saying it's larger or it's got more energy levels. The second mark would be along the lines of saying that those extra energy levels mean that the electrons are further away or there's more shielding. And then the last mark would be, therefore it's easier for them to be, for the electrons to be lost. Question 2. 6 marker. Again, people either know this one or they don't know it. Break it down into 3 nice easy bits, explain what's going on with the plum pudding model, then go on and explain about the nuclear model, and explain how you went from one to the other. So the plum pudding model is where there is a solid mass with an overall positive charge with negative electrons dotted through it. That was J.J. Thomson that came up with that when he discovered the electron. The next step in the development was that Rutherford and Marsden were shooting alpha particles at gold foil. They were a bit surprised because the alpha particles passed straight through in the main. Only a very small number bounced back. This led to the conclusion that it must be a very, very small nucleus, with most of it being empty. The third bit you'd be then saying is what the new model would be. So the nuclear model had a nucleus in the middle, small dense nucleus with a positive charge, and the electrons round the outside. What we are ignoring is anything relating to the work of Niels Bohr, which explains about energy levels and orbitals and things like that, because they're not relevant to this question. Okay. For question 3, you had to put 2 in the first orbital, here and here, and then you had to put 3 in the next orbital to give you 5 electrons, which you would have found from looking at it on the periodic table, looking at its atomic number, the smaller number. For Z, it's labelling the nucleus in the middle. It should be an easy mark for you, hopefully. For part 3, you get a mark for saying protons and neutrons, and you will also then get a mark for giving the relative charges. So neutrons have got a charge of 0 or a neutral, and protons are positive. If you start writing about electrons, you're going to start subtracting marks from yourselves here, because it is not asking about electrons, it's asking what's in part Z. That might be why you've got less marks than you might have expected. On part B, the electronic structure for neon, we're correcting it. So the first thing that you spot is that there's more than 2 electrons in the first one. So the correction would be you should only have 2 electrons in the first orbital. The next thing you might say is you can have up to 8 in the second orbital. And the third thing you'd say is the configuration would be 2.8. Or you'd add on an extra electron, because there's only 9 here in this diagram, but in the actual diagram, because it's a noble gas, it should have a full outer shell, so it should be 2.8, it should have 10 electrons in total. So in this one, done quite well on this one. It does say name 2 elements, so if you wrote the symbols, you're only getting 1 of the 2 marks, because it tells you to name it, so write the name. And we could have had anything from hydrogen, copper, or silver. The other ones are in group 1. Lithium, sodium, potassium and rubidium are in group 1. Which group of elements is missing? Here you could have the options of writing group 0, group 8, the noble gases, because they're all the same thing. You could also have the transition metals as well. For part C, a well answered question usually, why did Mendeleev leave gaps? It was for undiscovered elements, so they could fit his pattern still. It's one of the reasons why we like his periodic table. For part D, they're arranged in atomic number or proton number. For question 5, there are 4 gaps here on the table for you to fill in. So first of all, fluorine's proton number, you can either get this by looking at the periodic table that you're given, or getting the 2 and the 7 and adding them together and get 9. For the electronic structure of chlorine, we're just getting this 17 and breaking it down into the 2, 8 and the 7, which adds up to the 17. And for these, we're looking at this information here, and at room temperature, is it warmer than the boiling point? Yes, it has, so it will have boiled and become a gas. At room temperature, is it warmer than the 59-degree boiling point of bromine? No, it's not. Is it warmer than its melting point? Yes, it is. So it's melted, but it's not boiled, which means it must be a liquid. And that follows the trend that we should know for group 7, that it starts off with a gas, goes through bromine, which is one of our only liquids on the periodic table of elements, and then we go into a solid iodine. When it says the trend in melting points, you have to make a comparative in your statement. So you can't just say it increases. You could say as you go down the group, the boiling point increases. And notice it does, the number gets less negative, less negative, less negative, and more positive as you go down. Why the reactions of these elements with hydrogen are similar? So because they're all in the same group, they have the same number of electrons in the outer shell, which is 7. And that means they would all like to gain 1 extra electron. So if you said they've all got the same number of electrons, add in that they would like to gain 1 more electron to make a full outer shell. For part 2, you get a similar answer as what you had before. When we're looking at the reactivity decreasing from fluorine to iodine, again it's about the size. For these non-metals it's the opposite. So iodine is getting larger. The larger radius means that it's further from the nucleus, it's got more shielding, just like we were saying before for the alkali metals. The difference here is rather than losing electrons, it means it's harder to add extra electrons on. So it's similar but the other way around. For question 6, part 1 done really well. Just looking at the formula, it's Na2. So there's 2 sodiums there. There's no number next to the carbon, so that's just one of those. And there's an O3, which means there's 3 oxygens there. So the numbers in order would be 2, 1 and 3. For 6.2, you needed to add the 2 sodiums, the carbon and the 3 oxygens together. If you do that, you get 106. Most popular incorrect answers are where you're not adding the right number of atoms together. Other than that, whenever you see those, given the atomic masses like you are there, you just start adding them together, remember, ladies and gents. 6.3, thermal decomposition. 1 mark for each of the words that are in the quotes there. So thermal is heat. So if you said it's involving heat, there's 1 of the marks. And decomposition is about it breaking down. So ideally, you're writing a sentence like, it's a reaction where you're using heat to break something apart. For 6.4, explain why the mass decrease was observed. Just a quick reminder that in the test while Chardonnay was making her lovely remarks which entertained us all, it says 1.3 would actually mean 6.3. The equation above there shows that we've got carbon dioxide being given off as a gas. So the 2 things you'd want to be saying here is carbon dioxide is produced as a product, as your first mark. The second bit was that carbon dioxide would have a mass, so when it's lost, it would reduce the overall mass. And for 6.5, this is just a percentage question. So there's loads of different ways you can work out percentage. We want to find out what 40% of 1.25 is. So you can times 1.25 by 0.4, or you can times it by 40 and divide it by 100. Or you can work out what 10% of it is, which would be 0.125, and then times that by 4. But either way around, you should come out with an answer of 0.5. One little quick reminder when you're doing any sort of mathematical thing, just check that your number makes sense. So you're looking for 40% of 1.25, so you're looking for just under half of it. So ask yourself, does your number that you get in your calculator actually look like it's less than that? Because some people were putting numbers that were much bigger than 1.25 grams. On question 7.1, Remember, whenever you see those symbols and the numbers, you're going to start adding them together. So we've got 16 and 63.5 added together, making 79.5. There's your first mark. To calculate your number of moles, you're going to need to get your mass and divide it by the MR. So you've got to be careful you get this the right way around. It is 7.95 divided by 79.5, and that is 0.1. If you put 10, you put the numbers the wrong way around. It looks nicer and it seems more logical, but that is not the correct way of doing it. On number 7.2, to calculate the number of moles, in this case we don't need the mass is Mr. Moles formula, we need the formula for concentration. It's actually given in the units here. To work out that 2 moles per decimeter cubed, there was a number of moles divided by a volume in decimeters cubed. You're given a volume, but it's in centimeters cubed. So the first step, turn that 100 centimeters cubed into 0.1 dm cubed by dividing it by 1,000. And then to find out what the number of moles is, you'd times the 2 moles per decimeter cubed by the 0.1 decimeter cubed, which would cancel out the volume and just leave the moles. So 2 times by 0.1 would give you 0.2. The number 1 tip for both of these questions you just had, write down the formula for me first, then substitute in the numbers and then calculate it. If you just try and listen to it and go for it, then it's probably sounding like absolute gibberish to you. 7.3. It's common to use an excess. What's an excess? So excess is where there is more of one reactant. This means that you will completely make sure that the other reactant is fully used up and that there's nothing left of it. For 7.4, in this question you're given 2 numbers of moles. We've got 0.25 moles of copper oxide and 0.5 moles of sulfuric acid. Number 1 mistake, you added those together and you got 0.75 moles for your calculation. That's wrong. If you've got 0.25 moles of copper oxide, you can react it with 0.25 moles of sulfuric acid. That means that sulfuric acid is in excess. You've got more of that than you need. To take that another way, if you had 500 moles of sulfuric acid, you wouldn't have 500.25 moles of our product because you'd run out of copper sulfate a lot earlier. Okay? So first of all, if you got that the number of moles of sulfuric acid used anywhere in your calculations is 0.25 moles because there's the same amount of copper oxide, there's where one of your 4 marks come from. Okay, to work out the mass, it's the MR, which is the molecular mass, that's given to you, 159.5, times by the number of moles, so that is timesing it by 0.25. There's a second mark for you. That would give you 39.875 as the third mark. There is a command in there that says 3 significant figures. So when you're looking at this, in the 39, the 3 and the 9 are both significant. So that's your first 2 significant figures. And then the next number we'd need to round. So it's an 8 and the number after it is a 7. We'd round it up so it should be 39.9 to 3 significant figures. That's your final mark. If you've got any questions or anything that you'd like to go over on this test, feel free to see me in the new year. If not, have a fantastic break.